Yesterday, let me do a little summary of what we have done yesterday. So yesterday we introduced the perturbations of the metric tensor. We saw how to change how the perturbations for the metric were changing in the presence of a change of coordinates. And then we were able to then, having the way how the fields transform, first we discussed, let's say, 4 gauges, but actually the synchronous gauge I only mentioned, okay? I don't want to talk much about it. But the mostly 3 gauges I talked yesterday. So the unitary field, unitary gauge, where if you have an extra scalar field besides the metric, that one doesn't have fluctuations, but we need the field to be time-like always. And the longitudinal or Newtonian gauge, where this field becomes 0, and I erased this part actually, and the gamma was equal to 0. Actually, let me write again. Actually, let's see. Probably I put let's say 1 plus okay. So then yesterday okay, so the Newtonian gauge, these two fields are equal to 0. And then we discussed the flat gauge, where this field and this field were equal to 0. Okay. Yesterday we also saw that vector. We will see. Maybe, hopefully, we will see today the reason why vector, tensor, and scalar do not see each other at the linear level. Actually, what I want to do today is discuss a bit more about these gauge invariant fields. At least I want to start with that. Yeah, remember that yesterday I said gauge invariant fields in cosmological perturbation theory is just trying to find a linear combination of fields so that this linear combination of fields does not change under a coordinate transformation. By the way, yesterday one of the students asked me, so but how do I know whether, how do I know which gauge can I choose? And how do I know when one gauge is good or not? Okay, that's also a good question. No, now there is no simple and general answer to that, okay? The point is that this linear cosmological perturbation theory is a perturbation on the background. So what we assume here, we assume that we know what is A of t. So in other words, the background should be something that we already know. It's like exactly, the example I was talking about. I need to know what is the equilibrium position of the mass and the spring in this gravitational field. Otherwise, I don't know how to do this study of perturbations about this equilibrium position. Then, for example, suppose I have then means that I have to I had to know a knowledge of the background. Now, let me give you an example. Suppose that okay, let's start with a very simple case. Okay, suppose that I study three-dimensional elements of work in vacuum with no curvature, no cosmological constant. Of course, okay, so the background sets H to be 0. Then it's clear that the flat gauge doesn't have any meaning, because I cannot set delta phi to 0, because delta phi becomes gauge invariant. Okay? So it's the background who is telling me what to do somehow. Now, for this background, I can choose the longitudinal gauge. Okay? Because delta chi is, delta chi and delta gamma, I can always set to be 0. Because A is different from 0. This one just says that A is constant in general. What about the unitary gauge? Can I choose it? Well, I cannot, because as you can see here, I have only gravity. I don't have any extra scalar degree of freedom. It doesn't make even any sense to introduce a unitary field gauge, because I don't have any scalar field. Okay, so this background is pointing to longitudinal gauge. Now let's see what happens in this case. Suppose that I have a cosmological constant. This is a very tiny distinction, okay? Because I didn't introduce any scalar field. So once more, unitary gauge doesn't make any sense. Okay? This is cosmological constant. There is no scalar field inside this game. Now, H will be different from 0. H equal to 0 is impossible, actually, as long as this guy is positive. Okay, so then the flat gauge becomes a possibility. Newtonian gauge, yes, I can also choose Newtonian gauge. So now, for the first time, I have two possibilities. Which one you like, you choose. Because they are both, all the time, well-defined. Okay? Now, suppose we have this. Now, you may recognize this one as the Friedman equation in the presence of cosmological constant and in the presence of a quintessence field. Okay? Now, this would be if in the Lagrangian I put something, in the Lagrangian I put minus 1/2 d mu phi square minus potential phi. Okay, so if I take this Lagrangian here, this will be on three-dimensional elements of work plus gravity, okay, plus the standard gravity action. Then I will get this equation motion. Oh, then it means now I have an extra scalar field phi. As long as I'm sure that phi doesn't have phi dot equal to 0, notice that the unitary gauge is well defined when phi dot, as long as phi dot is different from 0. So how do I know? Well, I had to solve this equation. I had to solve. And then I will know what is phi of t. If phi of t is always positive, negative, or whatever, then it's fine. If phi dot will have a 0, then I know that that point will be bad. Okay? Let me give you another example. Suppose I have phi of t. I solve this equation and I have phi of t. Okay? And somehow I know that t naught is today time. Okay? then I have my field behaves like this. So this speaking, phi dot becomes 0 here, which is far in the future. We don't care. So it's not that, point is, yes, here the gauge will not be well defined, but I don't care because we don't have any data that point, billions years later. So as long as all my, in the present, in the past history, I care about. Okay, so say from recombination or whatever time up to now. If during that time phi dot was different from 0, the unitary gauge is a well-defined gauge. If that's the case, now we have 3 possible choices. Which one we take? Again, this is okay. So if all the gauges are well defined, the physical answer will not be different. Okay? As long as the gauge is well defined. Okay, so you don't, as long as you know that one of the gauges is fine, then you can use it. Okay? All right, so this was one of the questions here. And I think I wanted to. Now, let me actually say another thing. So because for example, delta phi becomes a gauge invariant is phi dot equal to 0. Okay. So remember, like this thing gauge invariant, I think was minus h divided by phi dot delta phi. You see, this one already tells you that this field should have is not well defined when phi dot equal to 0. It's a bad sign. So if that happens, never choose the unitary gauge. It would be a really bad choice. Okay, now I said this is phi gauge invariant, okay, which is true actually. If one studies what happens there, we find this field is gauge invariant. However, let me put gauge invariant, comma u, where u means the following: this field becomes phi in the unitary gauge. When I say in unitary gauge, I immediately say phi dot is different from 0, okay? All right? Now let me study phi gauge invariant in longitudinal gauge. What does it mean, this thing? This means so as I said, we need to consider linear combination of fields. Here I use this one and this one, but I don't need to use those 2 fields. Okay, for example, I can use lambda 1 chi plus lambda 2 gamma plus lambda 3. Oh, I don't want to put lambda 3. I had to, but I don't want to put. So what I'm writing here, I'm writing that I try to build up a field which is gauge invariant out of these 3 fields. Don't need to be 2 actually. So then it means then we have to see delta phi changes with this. Okay, so delta phi requires xi naught, and xi naught is in delta chi, which means that one linear combination will be gauge invariant. But delta chi also has this xs, but actually it has xs dot. Then with delta phi and delta chi only, I cannot remove completely the gauge, because I will always have xs dot. So the only way that I have xs is delta gamma. But notice delta gamma is not dot. So in order to have a gauge invariant combination here, I have to put also lambda 3 gamma dot. Okay? Now, what happens in that case here? So let's study how. Notice that this linear combination, both fields only require xi naught. That's why I was building up a simple gauge invariant combination. Okay, so this will be, so let me try what is delta phi, gauge invariant in longitudinal gauge. Notice, why do I say longitudinal gauge? Because in longitudinal gauge, I know that gamma and chi are equal to 0. So in longitudinal gauge, this will be 0 because gamma is 0. Not only one point in space and time. It's 0 everywhere, also in time. So also gamma dot will be 0. The 0, 0, 0, phi. So this field, this gauge invariant combination, which is different from, these are different objects, okay? These are completely different objects. One reduces to phi in longitudinal gauge, and the other one reduces to phi in unitary gauge. But they are not the same field. Okay. Okay, so then delta phi gauge invariant, what do? We have to do delta phi, and delta phi will introduce, where did I write it? Okay, minus h c0 plus lambda 1. Now I have to do delta chi, and delta chi will be c0 minus a square lambda 1 cs divided by a square dot. And let's see, now I have a plus lambda 2. Does it make sense what I'm doing here? I am just replacing each delta with the way they transform there. So delta phi was minus h xi naught. Then I have plus lambda 1 delta chi. And lambda 1 delta chi is lambda 1 times xi0 minus a square lambda 1 times the derivative of xs divided by a square. Plus lambda 2, I had to put delta gamma, which is minus cs divided by a square, plus lambda 3, and then I have a the dot of delta gamma, which is minus cs a square dot. Okay? If delta gamma transforms as such, the derivative will transform as in this way. Now you can see that we can indeed make it 0 if we set lambda 2 to 0. Okay? Lambda 1 must be equal to h. So then this one vanishes. Okay? And now lambda 1 has become h. So lambda 3 must be equal to a square h. oh, yeah, sorry. Minus. Minus, minus, minus. Okay? All right. Okay, so fine. We have our expression of phi gauge invariant. What? So there was a minus a square minus square h of Zs divided by a square dot. There is a minus here, minus, plus. So lambda square must be minus, minus. What's happened? Okay. All right. So let's say h delta chi will give me minus a square Cs divided by a dot. Okay? And then I had to add the plus lambda 3 delta dot, and delta gamma dot is minus times Cs divided by a square square. Okay? No? Yes or no? Yes. Okay. So they are both minus. I want this one to be 0. So lambda 3 must be minus. Okay, that's why I put minus a square h. Okay. All right. So we have these two fields, and let me write once more. Phi gauge invariant in the longitudinal gauge is different from phi gauge invariant in the unitary gauge. Okay? There are two fields which are different. Okay? Right, right.
But I mean, if it is the longitudinal gauge, then we set chi nu equal to 0.
Yeah. So here I'm not, okay, so at this level there, I didn't fix any gauge. What I'm saying, this field will be gauge invariant, so all the observer will agree with this field. And in particular, in the Newtonian gauge, this field will be equal to this. That's all what I say. Okay, so I don't need to find this one. So suppose I use a unitary gauge. This is the crucial point of the gauge invariant fields. Okay, suppose I chose in my discussion I chose the flat gauge. Okay, then the flat gauge is not the longitudinal gauge. But then some astronomers said, look, I found these very good constraints on phi in the longitudinal gauge. Oops, I said, I have studied my phi in the, you could have told me before, because then now it's too late. I did 20 pages of calculations in the flat gauge. No problem. Because in the flat gauge, the astronomer has studied this field in the flat gauge. Because in the flat gauge, phi and gamma are equal to 0. Okay? So the astronomer in my gauge have found constraint on this field. This thing must be clear. If it's not clear, please let me know. So the crucial point of these gauge invariant combinations is that, okay, some guy can put some bounds, or somebody can discuss something about one field. Usually, to be honest, the longitudinal gauge is used by, by experimental people, actually. So many times they have bounds on these fields in longitudinal gauge. Okay, so then do we have to use the longitudinal gauge? No. And the crucial point is that because we have gauge invariant combination, if the guy who studies longitudinal gauge, the astronomer, says, I use longitudinal gauge, and my constraint for phi is something, very well. This means that he has studied this field. And in my flat gauge, this corresponds to this one, on flat gauge. And what if I have used the uniform field gauge? Well, in unitary gauge, now this one will remain. Okay? When I say this phi, this one will be phi in unitary gauge, this one will be in unitary gauge, and this will be in flat gauge. Yeah?
Altogether, how many independent field I am allowed to keep after fixing my all gauge fixing that count it?
Good. You have to keep all of them. Okay? So, the two possibilities again here. You keep all of the, you fix a gauge. So you remove two scalars, for example. You remove two vectors. Two vectors means one vector with two components. You remove the vector, and that's all. And you simplify as much as possible your metric tensor. Okay? You cannot do anything else. Two scalars, yeah. So one vector, but each vector has two components, like two components for the vector, and two scalars. This is the most you can do. After that, you cannot touch anything else. Okay? Another way you say, another way that, okay, I don't really suggest you to do this second way, although it's a very good way to learn these things. The second way would be, I don't fix any gauge, anything. I bring with me all these fields, all. Then, at some point, I define gauge invariant combinations. Okay? And then I should be able to, even I didn't fix any gauge, to reduce myself to only gauge invariant quantities. This is a very complicated thing. I'm not expecting you to understand this one because there are some calculations behind this one, actually. But say that sometimes, no, okay, maybe I will tell, now I don't want to tell. It's a bit too complex. You need to see something in maybe with Maple. When we do Maple, we'll see. So in principle, you can keep all the fields with you, and then at some point you start defining gauge invariant combinations, and then you try to put all the fields you have in gauge invariant combinations. If you do that, then this gauge, will, whatever leftover gauge, they should remove automatically. So that's usually done when we want to check whether the code is correct. All right, so, okay, so let me say, okay, notice that I have studied this phi gauge invariant combination and this other phi gauge invariant combination. So if somebody says, you know, for this metric, phi is unstable. Strictly speaking, this thing, you have to say which phi. Either in which gauge or which gauge invariant combination you are talking about. Because to say phi doesn't mean anything. I mean, these two fields are different. it's possible this could be stable and this could be unstable. Okay? Because there are different fields. It's very clear in the flat gauge, right? In the flat gauge, this is 0. One is delta phi. And the flat gauge, this is 0 and this is 0, which is chi. So one is chi and the other one is delta phi. Completely different objects. They don't know each other, actually. Okay?
So when they will be equal in Newtonian case?
In Newtonian case, no, they will never be equal, in general. Unless very particular case, it cannot. If they are equal, this means that there is a non-trivial relation between delta phi, chi, and gamma dot.
Yeah.
This should be, so maybe some equations of motion should set this one, actually.
No, if we take
You see,
if we take h is equal to 0, but can we take
no, hold on a second. So these are gauge invariant combination. I cannot set a gauge for which they are equal. Because these are gauge invariant. So if they are equal, it's because the equations of Einstein equations of motion set it to be equal. But not because I made a particular choice of coordinates. So I need some constraints from equation that set this one to be equal, because they are gauge invariant. These are untouchable in a sense.
no, but if h is equal to 0, the both of these equal to phi, no, h is equal to 0 means a dot equal to 0. And that means a is equal to constant.
Now, h equal to 0, so that means that, okay, h equal to 0, this thing is not well defined.
Oh, yeah, that's
Because this is, well,
but phi dot equal to 0 is not well defined.
yeah, it's true, actually. Yes, okay, so h equal to 0, this is still, okay, good
And
one.
here also h equal to 0, these two terms will go. But we mean h is equal to 0, a dot equal to 0. That means
No,
a
hold
is
on.
equal to
Hold on.
Yeah.
Hold on a second. If h is equal to 0, we are talking about Minkowski. And the scalar field of Minkowski cannot have phi dot equal to 0 in a Lorentz invariant way. So the unitary gauge will not be well defined. Okay? So it's the background was telling me. So usually Minkowski, h equal to 0, longitudinal gauge is the only way, which is this one. Now this would be a perfectly fine, well-defined field, even when h equal to 0. In this case, this thing becomes this, because I know that delta phi becomes gauge invariant on Minkowski, because delta phi becomes 0. Okay. No, so this is the first thing that I wanted to stress, this thing. Then there is another thing that I want to say. Notice I have studied phi. But we have many other fields. So can I build up alpha gauge invariant? Alpha gauge invariant. Alpha gauge invariant. Yes, we'll have this chi 0 dot, right? So I need to use, say, for example, this one. Okay? So that looks like I have to do alpha minus delta phi divided by phi dot. Okay, minus because they have both minus. So xi dot will simplify. Okay? Delta phi divided by phi dot now transform as minus xi naught. You can also use delta chi. Now this will be, okay, so notice this alpha gauge invariant reduces to alpha in unitary gauge. Notice that phi dot must be different from 0. But, so let me put U. Gauge invariant, longitudinal gauge. This one would be, so again, I have to use the fact that This is a bit more complicated because you see that I need xi dot, so I have to take the derivative of this thing. So I will have to put plus chi dot. But plus chi dot will introduce some non-trivial derivative here, so which I will need xs double dot. So I will need gamma double dot. Okay, but it's possible. So it's always possible to build up this gauge invariant combination. Okay? Okay, maybe this one I'll leave you as an exercise. So once more, I studied, say, phi gauge invariant, alpha gauge invariant. Any field you can do its gauge invariant combination with different linear combination of fields.
The alpha gi comma L will reduce to alpha in the longitudinal gauge.
Great, very good. Because this will be alpha plus, say, k dot plus, say, gamma dot plus gamma dot, I don't know, plus gamma, something like this, okay? And then, of course, in the longitudinal gauge, this will reduce to alpha. So notice that the way I do it is the following, which is always a self-consistent thing to do. When I want to set a gauge, say longitudinal or unitary gauge or flat gauge, I have always to fix two fields. Okay? For example, in flat gauge, I fix phi and gamma. And one of the two fixes xi naught, and the other one will fix xs. And then, because it's a good gauge, this means that xi naught can be a I can write xi naught and xs in terms of the other fields. So I can, out of these two fields, I can always build up gauge invariant combinations. Okay? Because it's a good gauge. Because it's a good gauge. For example, suppose that I want to write down. Suppose that I want to write down delta phi gauge invariant synchronous gauge. And then it becomes a bit tricky because this one, delta phi, so this one will be, say, delta phi plus lambda 1 alpha plus something else. And I have bit problems here because this guy will get xi naught. And this one will be xi naught dot. It looks like impossible. And it's impossible because the synchronous gauge does not fix xi naught. Okay? Of course, then you may say, then you define delta phi dot. Delta phi dot seems to be better. But delta phi dot will not be delta phi what I wanted. So I can do this gauge invariant combination out of fields which I can uniquely set to 0 through a gauge choice. Phi and gamma, gamma and delta phi, gamma and chi.
Can you repeat this phi gauge invariant unitary and longitudinal gauge goes to 0? I mean, what is the problem?
Right, so here I am assuming there is an extra field, right? Delta phi. So again, I will have my background equation motion. Then this one is 0. How to get this? This one is 0. Phi dot. This must be true always, right? Right, so the solution is v of phi 0 equal to 0 and phi dot equal to 0. This is a good solution. So so then this one, the background implies that you cannot choose the unitary gauge. So again, it's the background which tells you. It's not you. So the background will tell you which gauge you can choose. Then it's up to you which one you want to use. Okay? this crucial point of the gauge invariant combination is that even you study your problem in one gauge, you will know how a field in another gauge will behave by using this gauge invariant combination. Okay? This happened many times. Okay? This happens many times. As long as the gauge is well defined, no problem. Okay? Okay. All right. Now, probably I would say that these gauge invariant fields, probably I can stop here for this gauge invariant. I don't have any other points in my mind to say about it. However, I would like to introduce introduce another gauge, which is also well used. Right. Right. So let's. After this, okay. So I'm going to introduce another gauge. Okay. Which is called the matter comoving gauge. I had to do it because it's a well-defined gauge and it's also very useful, to be honest. Okay, so now suppose that we have a perfect fluid, and then I just give you the expression of T mu nu. I choose to be up and down for reasons will be clear later on. I will get this one. Okay, so this expression here is a general T mu nu for the perfect fluid in any background. Okay. Now, let me suppose I want to find what is the variation of this field. Okay, here by variation, I really consider like taking this one, and then I perturb a little bit, and then I take the difference. This will be this delta T mu. So then I have to do this will be delta U mu times U nu rho plus P plus U mu delta U nu rho plus P plus U nu delta rho plus delta P plus delta P delta mu nu. And delta mu nu is just the Kronecker delta, doesn't have any delta. Okay. Now, then I want to look what is delta T 0 I, the 0 I component of this variation. Okay, let's see. So then mu must be delta U0, and this will multiply UI rho plus P. But if it is small, this must be background, so this will be 0. Does it make sense? This is a small quantity, say perturbation quantity. So this must be at the linear level. This must be order 0. So this must be background. But this is the I component of the vector. And the I component must be 0. The only component U that I may have in a isotropic homogeneous universe is U0. Okay? Good. So this will be 0. plus, let's consider this one, u0 delta ui rho plus p. Now, this is not 0, okay, because u0 is different from 0. Delta ui is a perturbation, so it doesn't need to be 0 on the background. And rho plus p is something. Plus, let's see what okay, then I will have this one. Again, this will be u0 ui. But ui is 0. And now I'm taking 0i component. So this is also will be 0. So the only thing that remains out of this variation here is this object here. u0 rho plus p delta ui. Okay? Now, remember that u mu is minus 1. And the G00 component is minus 1. This means that on the background, u0 is 1. And u0 down will be minus 1. Okay? That's the only non-zero component, given the fact that the G00, we chose to be minus 1. If it's not minus 1, there will not be this one. Okay? Does it make sense, this thing? This one, I just write it as u mu, g mu equal to minus 1. And you see this is ui equal to 0. The only thing that on the background, because this must be background quantity, on the background remains is u1, u0 equal to 1.
Can you just repeat it why the first term would be 0? Because the perturbation is there and then
Now, this is perturbation, right? So now I take the I component.
I component.
So this must be
Okay,
u mu on the background. Let me put the background like this. Is 1, 0, 0, 0.
yeah, that's right, yeah. But I doesn't go for means from 1 to 4?
No. I here goes from 1 to 3, and this
1
is
to
0.
3, okay. Oh, okay.
So I am considering the time component and the spatial component.
Spatial, okay. Then it's okay.
Then this is 0, everything else was 0. Now this one then simplifies to be rho plus p delta ui. Okay? Now then I name this delta ui. Delta ui will be a perturbation field, we expect, right? This one. Because we have ui, 0i. And again, ui is 0.
Yeah, I is running from 1 to 3.
1 to 3. And then this is 0i. Of course, this is chronicle delta. This is 0. So the only term which remains is this one. It's a very simple expression, if you think. Many things were. So I make a definition here to be minus rho plus p di of v. Now, you should raise your hand and say, no, this is impossible. Teacher, what are you doing? Because you are very kind. You don't want to say that. Okay. I accept this one. No, the delta ui, remember that u alpha is a vector. It's a 4 vector, right? So we know that the ui will be u0 and du of u plus u vector I. It's always the same thing, right? So I have a 4 vector, the 0, 0 component will be a scalar, and I have now the three part of it, which will be the di of a scalar plus a vector component. Now, but here, as you see in this delta ui would be this one, right? Because delta ui here, this is all, well, okay, so this is u alpha up, okay, all right? But say, so delta ui, what I call there delta ui, will be functions of this part here. So we should expect it to be a vector component there. So what I wrote here is actually only related to the scalar part of it. Okay? So when I write this one, I am automatically assuming I am only considering the scalar part of the perturbations. But this one should have this kind of thing in general. Okay? But this one for now, I forget. I'm not going to discuss about tensor mode, vector modes. Okay? Because I want to introduce a gauge again for the scalars. All these gauge things are usually related to the scalar modes. Although we have vector modes which can be gauged way, actually, remember that yesterday I said that a good gauge choice for the vector mode is this one. Okay? We can set the Ci to be 0. But here, let me allow to study only the scalar. The reason why I want to study the scalar mostly, not because I like scalars in a particular way, because usually they are the most complicated calculation to do in the scalar. Because you have many fields. You have many more fields, many more scalars than vectors. We have only one tensor. We have only one Hij for the tensor. We have 1, 2, possibly three vectors if you have some matter fields. But we have a bunch of scalars here. So we would expect the scalar to be the most complicated analysis. Indeed, it is.
So physically what do you mean that delta T0I? That means perturbation.
Right. This is a perturbation, right?
Yeah, perturbation.
So this means that I'm just making a field definition here. So this was a perturbation field, and I call this perturbation field delta I of it, actually with a minus.
And rho and P are all the same from the background.
Right, so these rho and P are background quantities.
Yeah, background quantities.
Okay, by the way, so let me say something which is unfortunately misleading, but I wanted to point out here. When I write this expression here, rho and P are not background. Rho and P are completely general functions. Can be function of t, x, y, z, and so on. When I do the delta t, then it's not true anymore. Because this one is supposed to be perturbations, and whatever is left must be background.
Yeah.
So although I call it with the same name, in principle, I should put these kind of things, background, everything background, no, this one, no. No, well, delta mu doesn't have background, okay? So I don't do it just because I'm lazy. But notice that there is huge difference. For example, when we write, I have a barotropic equation of state, this is not background. This is true at any order in perturbation theory. This can be a general function of t, x, y, z, anything, and in any background, not only in three-dimensional method of Winsor-Walker. And this will be the relation between P and rho will not change. In particular, for dust, P will be 0. And this is not a background thing. It's not that P is 0, but delta P is different from 0. Impossible. P equal to 0.
Why we are having a negative sign in this?
What's that?
Negative sign is there. You write P equal rho plus P delta, y equal to minus m rho plus P.
Delta T 0 I.
Yeah, the last part you are introducing minus sign.
Yeah, yes.
Yeah.
Why am I introducing this?
No, I understood this part of the negative sign.
Delta U
You are writing it a negative sign. It's a minus sign.
I just defined delta ui minus the IV. By definition. If you put plus, means your V will be opposite sign with mine. Okay? It's just a theory definition.
But you cannot just put delta UI only.
Yes, I can. Huh?
Why you are introducing another V? Means another field or
No. 1 second, okay? delta ui will be something.
Yeah.
Okay? This we will write in a second probably what is delta ui. And I will show you that it's possible to introduce delta iv. So far, let me give it as a definition.
Not exactly the same as decomposition, because there is only ui plus del ui.
Yeah. I will show you. Give me 10 minutes. But that's not a gauge choice, that's just a very definition.
What we are trying to find is the variation in the time components of the distance.
No. I'm trying to see what is the perturbation of this one. The perturbation of this thing out of a three-dimensional method of Benz Walker.
The question is that we got it as an actual expression to be rho plus p delta mu ui. Okay? That's one part. And then we decomposed ui into a scalar part and a vector part. We wrote it as a addition of the divergence and the vector part.
Give me 10 minutes and you will understand.
15 minutes.
15? Okay. You are patient. Good. Okay, so we will. The only point that so this is like how can I say? Showing before. So how can I say? It's. We will see in a moment that this is the case, that delta ui reduces to this kind of thing. But this just to say that we will see that this comoving gauge is setting v equal to 0. Okay? So what is comoving matter gauge? V equal to 0. But v equal to 0. Now, usually in electromagnetism, this will be the Poynting vector, T0i. So it's like how the energy, so there is this flow of energy, right? Yes, there's 0i, I0, yes. This is really Poynting vector. Okay, let me call it with its own name, the Poynting vector. So we are setting the Poynting vector in the scalar sector to be 0. Okay? So we will see that this one, because it's related to delta ui, is the speed, is the perturbation speed of my fluid. So if I set it to 0, it's like the fluid is not moving in that frame. That's why it's called comoving matter frame. Okay? Now, the other thing that I wanted to say, this one. Okay. Now, of course, I can set v equal to 0, but only once. So what I mean? Suppose that you have different matter fields. So you have a radiation, so you have a perfect fluid for radiation, then you have dust, so you have another fluid for dust, and maybe, well, usually these two are enough. Maybe baryonic fluid, whatever. You can choose this v equal to 0, but only for one of this. Only for one. You cannot choose for all your fields. Okay, so if you have a radiation gas, dust, and baryonic fluid, only if you want to choose matter comoving gauge, you can choose it only for one of these, not for all of them, because there are different fluids.
So speed v is with respect to Hubble flow. No, the speed of fluid with respect to Hubble flow.
Right. So yes, this is to respect to the observer, which would be at rest with the fluid, actually. So this is, yes, you're right. So if I am on the freedom electromagnetic worker, my galaxies for me are at rest, right? Because I don't have any v into this fluid, actually. But now delta v could be like a small fluctuation out of this. You know, galaxies are moving a little bit. This would be v. And then I choose that coordinate frame for which this fluid is actually not moving at all. But in order to do this, we have first to see what is v, and we have to see whether we can set this gauge. Okay? Notice that rho plus p for dust reduces to rho, And for radiation, reduces to whatever, 4/3 rho. So it's always positive, this quantity here, as long as we have matter, as long as rho is different from 0. OK, now we go to the question of delta. So let me use that part of the blackboard now.
So here you are taking time component, means that delta T0I.
Yeah.
But you will also do the same for space?
Yeah. No. Yeah, so in principle, yes, you will have delta T00, delta T0I, delta Ti0, delta Tij. You will have all this one.
Yeah.
But because I wanted to introduce the co-moving gauge, for me it's enough to say delta T0I. Okay? Now, let me go back to the question, what is this V? And can I write the delta Ui to be that object there? And we have to see also how it transforms. Okay? So let's do it. Now, we know what is U. Remember, I hope you remember all the first lectures on this perfect fluid stuff. We remember, I remind you that U mu was this, d alpha L plus theta d alpha S. And remember, I had AI, DI, d alpha beta, PI. Okay? And if you remember well, I said that these two fields were useful if I wanted to study the vector modes. In the notes, I explained these vector modes very well, but because here I already have neglected the vector modes, let me actually neglect the vector modes also here. So I will forget about this. Okay? So those are enough to study the scalar modes with thermodynamics. So then we can now study what is delta U. So let's say what is Ui, delta U alpha. This will be minus 1 divided by mu square delta mu. Okay, so I have to take the variation of each single term. So I will get minus u mu square delta mu times, I will have this, which is just mu u alpha. Okay, so this vector here is mu u alpha. Plus 1 divided by mu d alpha delta L, because the partial derivative commutes with the delta, plus d alpha S delta theta plus theta d alpha delta S. Okay? Agree? Great. Now let me study delta Ui. Okay, so this becomes Ui. Goes away. Because Ui, so this is perturbation, this must be background. Okay, now this one, background, background, background. Okay, so this one will not be there. This one is just background, so we will get 1 divided by mu di dl plus, on the background, remember, S was constant. Not only time independent, but purely constant. Actually. You remember we had this? Yes. Okay. So this goes away completely, and theta is a function of time. Remember that theta dot is equal to t. So then this one is theta delta S. But theta is a function of time. So this one is di theta S. Sorry, ti delta S. Okay, this is delta S. So delta S is not constant. Okay, delta S is the perturbation. Can be anything. But this theta was function of time, I can put it inside. So as you can see, and mu is also a function of time. So this one is di of delta L plus theta delta S divided by mu. And this, then I fix it to be delta IV, minus delta IV. So V exists. V is this really well-defined quantity. Okay? Okay, so we found that let me go to this other part of the blackboard. So, and notice, because I have neglected alpha and beta, because I told those were responsible for the vector modes, my delta ui is only a pure scalar, because it is di of a scalar. There are no vector components. But this is expected because from the beginning I removed alpha and beta. I can do because scalars don't see vectors. Okay, so then so we have that V is minus delta L plus theta delta S divided by mu. Okay, so this is a definition of V in terms of the other fields. Can I do? Yes. Nothing prevents me to do that. I can always do Fourier definitions. And when I say Fourier definition, linear perturbation theory means linear combination of fields where the coefficient must be background. Okay, so this is a background quantity, okay? And this is also background quantity. Now, we had to study how delta V changes according to a gauge transformation. Okay, now, so here, this will be 1 mu delta L plus theta divided by mu delta S. L? Ah, with a minus. You mean with a minus? L dot? No, there is no dot here. This is di delta L. No. This is imperfection in the blackboard. It was a dust dot, that one. All right, so then, so we have this one, delta L plus theta delta S. We had to find this kind of thing. Now, how do we find out how they change? Remember, for any scalar field, remember how to do it. Let me do it once more. So we had to find this. Delta phi will be phi of x minus phi of x. This is phi prime of x prime minus xc minus phi of x. This phi prime x prime minus d phi over d z alpha minus phi, and this is minus d phi over dx alpha z alpha. Okay, so this is how a general scalar changes under this coordinate transformation.
So do they have to satisfy some constant? Because at the first you said it will co-moving u alpha is equal to 1 not 1 0 0. Then you use this definition and so that this is so this I component also varies here also because you use that thing which
Okay, yeah, okay. So remember, so the equations of motion will tell us, right? So the equations of motion were, if you remember well, were this on the background, and the other equation of motion for the background was this one. Okay? So these were the constraints we were getting these were the equations of motion we were getting. In particular, now I evaluate them on the background. So this means that L dot when I say L dot now, I mean really not delta L. This is really background quantity, is minus mu. And this means that just S dot equal to 0. Okay? But then it means that this thing will have minus 1 divided by mu, and delta L will transform as minus L dot xi 0. Okay, because the only background quantity for my L is when I have time derivative. So this will select xi 0. Minus theta divided by mu, and this will be 0 times xi 0. Because S, if I do delta delta S, this will be minus S dot divided by xi 0, which is 0. Okay, and delta delta L will be minus mu dot divided by times xi 0, which is mu dot, L dot, minus L dot, L dot minus L dot xi 0, and L dot is minus mu, so we get mu xi 0. And yes. Okay? So the delta S, which is the variation of entropy, is actually a gauge invariant quantity for any fluid. We cannot set it equal to, so which means we cannot touch it. We can never set it equal to B0. But delta L goes like xi naught, actually. Seems a good field. And in fact, then the sum of these two will just give you, remember, L dot is minus mu, you will get minus xi naught. So delta V changes with minus xi naught. So it's a perfectly good field to set it equal to 0. No matter fluid you have. You may have dust, you may have radiation, you may have baryonic fluid, whatever. You can always set its V, which is delta Ui, the scalar part, to be 0. So it seems a good gauge. So then we can add to this one, we can add to the table that I wrote there, and I think then I probably, we can add here a final co-moving gauge, co-moving matter gauge, delta V is equal to minus xi naught. So essentially we put V old minus V old to be equal to minus xi 0. This is always possible to do. Notice that this one, usually when we say co-moving matter gauge, we fix xi naught in this way, and we fix xs still putting gamma equal to 0. Okay? Because this only fixes one of the two scalar. So the other one, again, gamma equal to 0. Should we stop? Why? Because if we don't, we are still some gauge degrees of freedom. Exactly. So this field changes only with xi naught. There is no xs. Okay, let me put your question another way, which may be useful to discuss before the end. Let me erase this part. So we found that delta ui can indeed be written as minus di of v. Okay? Now, of course, as I said, this is the scalar part. There will be some vector component which I am not neglecting, but I am considering scalars. So whether I put it or not doesn't change the results. Now, but we know that u alpha, let me put down, u alpha down, will be u0 and ui. Okay? So when I do delta u alpha, you would expect to have delta u0 and delta ui. To be, yes, okay? Then I say, what is this scalar here? Because I have another scalar. And I cannot use that scalar. Why? Or if you want, that scalar doesn't add anything new. Why? Who said that? Very good. That's exactly true. So this is not a general for vector. But it's, this for vector is supposed to satisfy these constraints. And these constraints removes one in terms of G alpha beta. So then this one can be written as u0 square equal to something. I mean, in principle, can be solved for u0 in terms of G alpha beta and maybe the ui. So then this scalar here is actually will not be a new scalar, but will be some combinations of all the other scalars. So then I don't need to study how it changes because it will be completely functions of all other fields. But this one is new. This object was new, actually. So then from a perfect fluid, I may expect this, delta p, delta rho, and maybe delta theta, delta s, something like this. But I know that what happens, they're all time dependent. For example, how does delta rho changes? And this is minus rho dot c0. Because I had to take the derivative, but this is only on the ground is only time dependent, so we will only select c naught. So the same thing happens for theta. So delta theta, this will be minus theta dot c0, and by the way, this is minus t c0. So all these objects here only deal with c naught. The only one that in principle could interact with that gamma was this point here. But the problem is that we just saw that V changes in this way. So again, C naught only. So then to fix CS, one needs to use the metric tensor. One can set gamma equal to 0. The gamma is a very useful field because we can use it to set it equal to 0, and we fix completely the gauge, CS. Okay, then I stop here.